The probability of a protein randomly forming has been calculated at 1 chance in 10 to the 160th power, up to 1 chance in 10 to the 243rd power, depending on the size of the protein. A simple bacterium, like E. coli, has 4 million base pairs in its DNA. The odds are about 1 chance in 10 to the 400,000th power that this would occur randomly. In short, you can't get one protein, much less an entire living cell, by chance alone. It's absurd. The competing theory to randomness is non-randomness. If the odds that an event is random is 1 in 10, looked at the other way, the odds that it's non-random is 9 out of 10. Sir Ronald Fisher was an evolutionary biologist, geneticist, and statistician. He's been described by Richard Dawkins as the greatest of Darwin's successors. And the historian of statistics, Anders Hald, said, quote, "Fisher was a genius who almost single-handedly created the foundations for modern statistical science." Fisher is the author of The Genetical Theory of Natural Selection, published 1930. This is the first book to provide a synthesis between Darwin's natural selection and Mendelian genetics. Many scientists contributed to the neo-Darwinian theory, but it was Fisher's work that made it all possible. This brings us to the second point, Darwin's natural selection. According to evolutionists, this is the process by which the most fit survive to reproduce. It follows logically that the survivors are the most fit. Now you have a problem. Why? Because the most fit survive, therefore the survivors are the most fit. The survivors are the most fit because the most fit survive. This isn't circular reasoning. This is true by definition. It's simply been defined as true and may or may not reflect reality. Let's consider the definition and see if it really does reflect reality. If an organism is more fit to survive in an environment, then the fitness must be reflected in the information in the genes. Let's consider the egg in a nest of 10 eggs that gets eaten by a predator. Was the egg less fit because it couldn't run, hide, or fight as well as the other eggs? No. Its fitness as an organism is irrelevant. It was simply a random incident. Genetically, it could have been the most advanced individual of its kind, and still it died through no fault of its own. It had a 9 out of 10 probability of not being the egg eaten in that nest, and it lost. It could just as well have died due to a lack of experience on the part of the parents. It could have died due to a fire, flood, drought, storm, or volcano. In practice, you can have the best genes and still not survive. Accidents do happen. The genetic advantages are small because change occurs slowly. Fisher used a 1% advantage in his calculations. Evolution is supposed to be gradual. Any one genetic mutation with a 1% advantage has a 98% probability of extinction. It won't survive. Therefore, it's not the mutation that's preserved, but the statistical norm. Those that represent the most common type, because there are more of them. It's not necessarily survival of the fittest, but survival of the most numerous. This is in fact in keeping with the original meaning of the term as used by Edward Blyth, a creationist. Francis Hitchings, an evolutionist, has written, quote, "Darwin took everything Blyth had said and used it to support an opposite conclusion," unquote. Blyth saw natural selection as the process that culled the weak and preserved the strength of the group. It's neo-Darwinian natural selection that does not reflect reality. We've looked at the egg, now let's consider the chicken with its 78 chromosomes. Evolution says that at some point in history, it was not a chicken. With only 76 chromosomes, it's not yet a chicken. Let's call it a hicken. With only 76 chromosomes, at some point it has to make the hurdle of going from 76 to 78 chromosomes. How would that work? By some miracle, a chicken pops out of an egg laid by a hicken? I'm not claiming that evolution occurs in a single step. That's the hopeful monster theory. Evolution's a gradual process, but at some point the offspring have to make the change from 76 to 78 chromosomes. So then, where's this chicken going to find a date? How many times must this mutation occur before two chickens got together? The odds they're the same sex, should they ever get together, is 50-50. This mutation would have to be repeated 50 to 250 times before a viable population of chickens was established. Fisher used these numbers in regard to any genetic mutation in a breeding population. However, the mutations were presumed to be able to breed with the parent group. That's not possible in our example. So this is a conservative estimate. Remember that it must be the identical mutation for this to work. This requires a very high rate of mutation, all to get just one new species with a different number of chromosomes than the parent. In fact, if every single mutation throughout history had to be repeated 50 to 250 times, as Fisher demonstrates, just to establish it in a breeding population, then we're going to have a very, very high rate of mutation. Which brings us to the third point, random mutation. All mutations are not created equal. What's needed for evolution is a mutation that improves the odds of an organism's survival. In addition, in order for human life to have evolved from a simple cell with only 3 or 4 million base pairs in its genome to the 3.1 billion base pairs in humans, useful information in the form of base pairs must be added by a mutation called an insertion. If each insertion adds one base pair, 3 billion different insertions would be required to go from the simple cell to human life. If each insertion mutation must on average be repeated 100 times, then we're looking at 300 billion insertions, more or less. And that does not include mutations such as deletions, transpositions, inversions, or amplifications, and mutations that did not occur in sufficient numbers to survive. If this occurred over a 3 billion year period, then you'd need some 100 useful identical insertions per year. That would just about establish one new insertion mutation with one base pair every year. This is just a ballpark estimate, but these numbers are taken from the literature and demonstrate the tremendous amount of useful material that must be added to the genome in a fairly short span of time.